Hello everyone. Welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you may refer to my GitHub page at this given link. In many lectures, we have been solved constraint optimization problem using Lagrange multiplier methods like support vector optimization problem or PCA, but we couldn't discuss in detail. So in this lecture, I would be covering the constraint optimization problem, which is also known as convex optimization problem, where the objective function is quadratic and the constraints are linear in the parameter. So if you will see the optimization problem, it has the format something like this. To minimize a function of x1, x2, x3 and x4 such that x1 into x2 into x3 into x4 is greater than equal to 25, x1 square plus x2 square plus x3 square plus x4 square equal to 41 less than equal to x1, x2, x3, x4 less than equal to 5 and x0 equal to 1, 5, 5 and 1. So these are the basically corresponding value of x1, x2, x3 and x4. So in this optimization problem, this is called objective function. This is called inequality constraint. This is called equality constraint. This is called bounds, and this is called initial guess. Okay, so a very well-known technique to solve a convex optimization problem, and that method is called the Lagrangian multiplier method. So first we will see how the Lagrangian multiplier method can be used to solve a constraint optimization problem. So in this lecture, particularly we will focus on the inequality constraint optimization problem and equality constant optimization problem, and where the Lagrangian multiplier method is very handy to solve this kind of optimization problem. So depending on the types of constant, there are two types of optimization problem. So the first one is equality constraint optimization problem. So in this case, we can define the constraint problem as minimize f x1, x2 and xd. So here f is the function of x1, x2, xd. We have to minimize this subject to some function of x which is equal to 0. So here we have p number of functions. So I equal to 1 to and the other optimization problem is inequality constraint optimization problem. So we can write our optimization problem as minimize f x1, x2, xd subject to function hix less than equal to 0. So here we have p number of functions. That means we have p number of equality constraints. Okay, so this is the second type of problem which can be solved using the Lagrangian multipliers. So one by one we will see these two constraint optimization problems. So first we will see the theory, then we will solve one problem on each optimization problem using Lagrangian method. Now let us see the equality constraint optimization problem. So to solve the equality constraint optimization problem, there are the following steps to solve. So in the first step, we define the Lagrangian as follows. So here what we do to define the Lagrangian, we add the weighted sum of the constraints with the objective function. So fx is our objective function. In the objective function, we add the weighted sum of the equality constraints where the weights are basically the lambda I, which is dummy variable and which is also called the Lagrangian multipliers. So we can write lambda I are Lagrangian multipliers. In step 2, we set the first derivative of the Lagrangian with respect to x and with respect to lambdas, and then we will set it to 0. Okay, so we can write delta Lagrangian equal to 0. So here we have I equal to from 1 to d, because we have how many variables? We have d number of variables. So we have to take the derivative of Lagrangian with respect to d different variables, and then we have del L del lambda I. So this is the derivative of Lagrangian with respect to different Lagrangian multipliers. Then here we have d plus p number of equations. We have d plus p number of unknowns. So we can solve this problem and we can get the value of x1, x2 and xd and lambda 1, lambda 2 and lambda p. Now let us solve one example. Suppose we have a constraint optimization problem minimize fxy equal to x plus 2y subject to x square plus y square minus 4 equal to 0. So this is the example of the equality constraint optimization problem. So you can notice here the constraint is in equality form. So this is the equality constraint. So let us solve this problem. So here in the first step we have to define the Lagrangian. So we can define the Lagrangian as Lxy lambda equal to x plus 2y plus the weighted sum of the constraint. So here we have only one constraint, so we can take the only one variable or only one Lagrangian coefficient and we will multiply with the constant. So this is our Lagrangian. In the step 2, we will take the first derivative of Lagrangian with respect to x, y and lambda and we will equate to 0. So when you will take the first derivative of the Lagrangian with respect to x, you will get 1 plus 2 lambda x to 0. First derivative of Lagrangian with respect to y is equal to 2 plus 2 lambda y equal to 0 and the first derivative of Lagrangian with respect to Lagrangian coefficient lambda is equal to x square plus y square minus 4 equal to 0. So here we have three equations and three unknowns x, y and lambda. So we can solve these three equations to find the three unknowns. we will have two solutions for x, y, and lambda. And another set of solution is okay. So when lambda equal to minus root 5 by 4 and x equal to 2 by root 5, y equal to 4 by root 5, then we will get fx y equal to x plus 2i. This was our objective function, and for this value we will have 10 by root 5. And when lambda will be plus root 5 by 4, x equal to minus 2 root 5, y equal to minus 4 by root 5, then we will get fxy equal to minus 10 by root 5. So here this problem was the minimization problem, and here we can observe that fxy value is minimum for x equal to minus 2 by root 5 and y equal to minus 4 by root 5. So we can say that the function fxy has its minimum value at x equal to minus 2 by root 5 and y equal to minus 4 by root 5. So this is our solution of equality constraint problem. The next constraint optimization problem is inequality constraint optimization problem. So this method is quite similar to equality constraint optimization method. However, it introduces additional constraints called Karuskun-Tucker constraints. So which is very famous, and it is also called KKT constraints. The first step is define Lagrangian. So we can define our Lagrangian as, so here we have x variable and our Lagrangian coefficient. So here we have defined our Lagrangian as same as that we have written in equality constraint optimization method. Okay, in next step we write cross con together, which is KKT constraint. So it is del Lagrangian divided by del xi equal to 0. So here we have d number of equality constraints because we have d number of x variables, that is x1, x2 up to xd, and lambda I, that is Lagrangian coefficients, are greater than equal to 0 for all value of I, and the function hix is less than equal to 0 for all I, and the Lagrangian multiplier into the function, that is the inequality constraint. So hix is equal to 0, I equal to 1, 2, p. So solving these above equations, we can get the optimal value of fx. Okay. Now let us solve a problem on inequality constraint optimization problem. So here we have given a problem where we have to minimize fxy equal to x minus 1 square plus y minus 3 square, subject to x plus y less than equal to 2, and the other inequality constraint is y greater than equal to x. So how we can solve this problem? So in the first step we will define the Lagrangian here. Lagrangian is equal to the objective function here. The Lagrangian is equal to the objective function plus the weighted sum of the constants. So here we have the two constants, so we will have the two Lagrangian multiplier. So lambda 1 into the first constant so from this first constant we have to make it in the standard form, so it will be x plus y minus 2 less than equal to 0, and from this constraint we will have the standard form as x minus y less than equal to 0. So here the constant should be in the form of less than equal to 0. Then our Lagrangian will become lambda 2 into x minus y. In the next step, we will define the KKT constant. So we have to solve this Lagrangian subject to KKT constants. And what are those KKT constants? Del Lagrangian del x equal to 2x minus 1 plus lambda 1 plus lambda 2 equal to 0, because we have to take the first derivative of Lagrangian with respect to x. The other constant is the first derivative of Lagrangian with respect to y, and we will obtain as 2 into y minus 3 plus lambda 1 minus lambda 2 equal to 0. Then we will have the constant as lambda 1 into x plus y minus 2 equal to 0. Lambda 2 x minus y equal to 0. And here Lagrangian coefficients are greater than equal to 0, and also we have the constant x plus y less than equal to 2, and y is greater than equal to x. So these are the KKT constants. So we have to solve this Lagrangian problem subject to these KKT constraints. So for this we have to consider the different cases, like we can make here four different cases for different values of lambda 1 and lambda 2. So let us solve this KKT constant problem by considering the different cases. In case 1, we are considering lambda 1 equal to 0 and lambda 2 is also equal to 0. Then if we will put in the first constraint and in the second constraint, we will obtain our equation as 2x minus 1 equal to 0 and 2y minus 3 equal to 0. So if we solve with this, we will obtain x equal to 1 and y equal to 3. So when we compute x plus y, then we will get 4. But here we have one constant is x plus y is less than equal to 2. That means it violates the inequality constraint. So it is not a feasible solution that we considered. Now let us consider the case 2. In case 2, we assume lambda 1 equal to 0. However, we consider lambda 2 as non-zero. So if we consider the equation lambda 2 into x minus y equal to 2, so here we have considered that lambda 2 is non-zero, but this complete inequality is 0. That means x minus y will be 0. So we can write x minus y equal to 0, and from here we can write 2x minus 1 plus lambda 2 equal to 0, and 2y minus 3 minus lambda 2 equal to 0. So when we will solve these three equations, we will get the value of x as 2, y equal to 2, and lambda 2 equal to minus 2. And already we have lambda 1 as 0. So when we will check the condition that whether it will satisfy x plus y less than equal to 2, then we can find that it violates this constraint. But we have x plus y less than equal to 2. So it is not a feasible solution. Now consider the case 3. In case 3, we assume lambda 1 is non-zero, where lambda 2 is equal to 0. So when we will have this condition, then from this inequality you can check that lambda 1 is non-zero, so definitely we will have that x plus y minus 2 will be 0. So x plus y minus 2 equal to 0, and from these two constants we can write 2 into x minus 1 plus lambda 1 equal to 0, and 2y minus 3 plus lambda 1 equal to 0. So when we will solve these three equations, we will obtain x equal to 0, y equal to 2, and lambda 1 equal to 2, and already we have considered lambda 2 equal to 0. So if we will check all the constraints of the KKT, then we will find that these value will satisfy all the KKT constraints. So we can say that this is a feasible solution. Now let us check the case 4. In case 4, we assume lambda 1 as non-zero and also lambda 2 as non-zero. And if we consider these conditions, then we will have the set of equations x plus y equal to 2, x minus y equal to 0, 2 into x minus 1 plus lambda 1 plus lambda 2 equal to 0, and 2y minus 3 plus lambda 1 minus lambda 2 equal to 0. And if we will solve these four equations, we will get the solution as x equal to 1, y equal to 1, and lambda 1 equal to 2, and lambda 2 equal to minus 2. But we have the constraint that lambda 2 should be greater than equal to 0. That means this is not a feasible solution. So here we have seen the four different cases to solve the KKT constraints problem. So here if we consider the case 3, then we will get the solution of this given problem. So I hope I am clear to you. If you have any doubt, you can ask your doubts in the comment section. Thank you.